Okay, good morning. Welcome back. Let us get started. Today is September 28th. It's our 10th class of the semester. Today, the first project on arbitration is due. Go ahead and throw it in the green folder if you have it. Just a reminder of the policy laid out in the syllabus about late projects. I will accept them up to 1 week late. If you turn this project into me by Friday, you will get 5 points off. If you turn it in after that, you will get 10 points off up to 1 week. After 1 week, it is 100 points off. So turn it in within 1 week of now. If you turn it in, like 2 hours after class, it's still the 5-point penalty. So right now is when it's due. It's on time right now. After that, it's 5 or 10 points off. Okay. Today we're going to talk about interpreting derivatives. Next class on Friday, the second project is due, trucks. So hopefully we've got good progress made on that one. On Friday, we'll cover one more class of new material, the second derivative. Twice as much fun as the first derivative, which is great, right? And then that's the last day of new material before our test. Monday coming up is our review day for the test. I have no agenda on that day. It's just going to be you guys doing practice problems. And then on Wednesday, 1 week from today, is test number 1. It covers all of the sections we've done so far. Questions on the calendar, Levi? Yeah, there's a practice test in the back of the packet that we're working on. Yeah, I expect that's what most folks will be looking at on Monday in class. Other questions? Yeah, Matt? Yeah, you can make your own one-page cheat sheet to use on the test, front and back. Okay. Good question. Scientific calculator only on the test. I'll lend you one if you don't have one. How big? 8.5 by 11. But you 8 in a regular piece of paper. 8.5 by 11. Do not come in with like a bulletin board.
I can actually write.
Yeah, you write as small as you want. Okay. All right. Okay, so we're starting on page 62. I do have quizzes to give back, and I will give them back in just a little bit today. I did want to talk briefly about the quizzes, but we've got a few folks out. I'm going to just wait and see if anybody straggles in before we talk about the quizzes. So let's jump in here to our daily summary up at the top. In this class, we learn different notation for the derivative, and we explain what the derivative represents in a variety of contexts. Number 1, this section is very notation heavy, but stick with it, and these unfamiliar symbols will become second nature for you with some effort. A brief history lesson. Calculus was invented/discovered independently by 2 folks, Wilhelm Gottfried Leibniz and Sir Isaac Newton. Both discovered calculus around 1660 AD. So here are the 2 protagonists of our story, Newton on the left, Leibniz on the right. It was actually, it's kind of interesting that you'd have these 2 people, Newton from England, Leibniz from Germany, who had very little contact with each other. Very little contact. There was like 1 or 2 letters that went back and forth between them, but pretty much simultaneously discovering this brand new field. And surprisingly, that happens kind of pretty often in math and in science. Calculus was an idea whose time had come in the mid-17th century. And to say that these 2 guys invented calculus isn't really paying tribute to all the mathematicians that came before. Lots of people who had pieces of calculus over the previous 1,500 years. I mean, Archimedes was doing some pretty good calculus stuff back in 300 BC. So anyway, but these are the 2 folks that we give credit for the final, putting the final pieces together. It actually became quite ugly in that there was some dispute over who should get credit for this brand new field, and this happened while they were alive, not posthumously. And it became, these 2 guys kind of stayed out of the fray, but it was really their supporters that kind of fought for who should get credit for the discovery of this new field of mathematics. You guys all know who Isaac Newton is, and I'm guessing most of you have never heard of Leibniz, and that's unfortunate because Leibniz should be right up there in terms of his work, his contributions to this field. Newton, of course, has done all kinds of other things in physics with gravity and stuff like that. But it's kind of sad. I mean, it became a rivalry between the 2 countries, England and Germany. Like Newton becomes knighted and is buried in some royal place in England. Leibniz's funeral is attended by only 1 person, his secretary. And so it was not a happy ending for poor Leibniz, but Newton's, like up there on the pedestal, Germany. The way that they wrote things was slightly different, and we're going to look at the differences down here. But essentially, they were both thinking slopes of tangent lines and realizing how they could use slopes of tangent lines like we've been doing for maximization and minimization problems. Yeah. Okay, so number 2, they made up different notation for the derivative. Newton wrote the derivative of x squared plus 7 as x squared plus 7 with a dot on the top. We do not use that notation. Leibniz used the notation dy dx, which we have seen a little bit this semester, to represent the derivative of y with respect to x. We have been writing this for the last few classes, and we've been saying that that represents the derivative of whatever's in the brackets. And the reason that Leibniz used this dy dx is that, well, let's see, we know that the derivative is the slope of the tangent line. And from before calculus stuff, we know that the formula for slope is change in y over change in x. Yes? What Greek letter are we using there? Delta. And so delta y, delta x becoming dy d. I mean, it's the same, right? It's just a different version of the letter d. And so Leibniz uses this dy dx notation to say, hey, it's just slopes. But in some sense, when you're using this delta y, delta x formula, you can pick any 2 points you want. So you might have very big deltas, right? Big change in y, big change in x. But when we're thinking about slopes of tangent lines, going all the way back to maybe the second or third class of our semester, if you wanted to find the slope of a tangent line, at this point, you would connect to a very nearby point and draw a secant line, right? And you would try to get that point closer and closer. And so capital delta, possibly big changes in y and x, lowercase d, possibly to signify really tiny changes in y and the corresponding tiny changes in x, or maybe probably say that the other way. Tiny changes in x and the corresponding tiny changes in y, okay? All right, so about a century later, the French mathematician Joseph Louis Lagrange invented the symbol f prime of x. Quite commonly, we'll use f prime, and we will also commonly use this dy dx. We will not be using the dot. Number 3, here are 4 things that all mean the derivative. F prime of x we've used. On the far right, y prime should look familiar as well. This is Leibniz's notation right here. And if we just kind of peel that y off, again, thinking of d over dx as the symbol that means the derivative of, we can just put a function y right there, and he just kind of pushed that y on top of the fraction, okay? So for me, this d dx is kind of a separate symbol from the y. It just means derivative of, and then the y is the function in this case. And so, of course, instead of a y, we can put f of x, just another name for that function. Levi. D, the function? Yeah, so I think that you could put that, and I think probably a lot of folks would recognize what that means, but you'd make it a whole lot easier on your reader to separate off. I still see this as one thing, even if it's right there on top. But even if the function x squared is right there on top, I still see the d dx as its own symbol, and then the y or the function as its separate symbol. Yeah. Okay, so number 4, one disadvantage of Leibniz's notation is that writing f prime of 3 is awkward. It's really easy to write f prime of 3 using the f prime notation, but using the dy dx notation, we actually saw one example of this the other day. You put this vertical line, and then at the bottom right, you put x equals 3. It's the same way, it just means f prime of 3, all right? Okay, number 5. Let's pause on number 5. So I wanted to talk briefly about the quizzes. Like I said, I will hand them back in just a little bit. But there were a couple of things that I wanted to point out about the quiz. Let's come back here to, where are we? Number 5. dy dx has units of the form y units over x units. Writing down what the units are for the derivative goes a long way in helping us understand what the derivative represents in some unfamiliar context. I'm hoping it makes sense. I mean, like, there's an easy way to just recognize, right? dy is on top and the y is on the top, and then the x is on the bottom and x is on the bottom. So, I mean, the pieces are in exactly the spots you'd expect them to be. But it also should make sense just because you know that dy dx is a slope of a tangent line. And the units for slope are y units over x units, right? Change in y over change in x. Said another way, the derivative has units of the form dependent variable units over independent variable units, in case the letters aren't x and y. Number 6, for example, if g equals f of t represents the cumulative number of gallons of water that have passed over a waterfall t seconds after midnight, then dg dt has what units? So the units we're looking for on top are from which letter? G. And what are the units for G? Gallons. Over, and the units for the bottom go with T, seconds. So the units for that derivative, dg dt, are gallons per second. So in some sense, we're getting a measure of how many gallons per second are passing over that waterfall. So in the context of the waterfall example, what do these two things represent? G of 30 equals 120. We'll start there. 30 what? 30 is the T, right? It's the input. So that's 30 seconds. After midnight. What are the units for the 120? 120 gallons. So we'll start there, 120 gallons. What about those 120 gallons? They have passed over the falls. It's a total, right? 120 gallons have passed over the falls. I'll put here in parentheses in total. Cumulative count. Okay, second symbol we're trying to interpret. dg dt, vertical line t equals 30 equals 3. dg dt is our symbol for the derivative. The vertical line says evaluated at t equals 30. So something's going on here at t equals 30 where the value of the derivative is 3. So let's again start this same way. T equals 30 still means 30 seconds after midnight. Okay, let's get some units for this 3. What are the units for the 3? Gallons per second. That's the dg/dt that we answered previously. So something is happening at a rate of 3 gallons per second. So in this case, the cumulative number of gallons is changing at 3 gallons per second. We have a word for this in the waterfall example. What is this 3 gallons per second describing about that river? Starts with an F. Flow, right? That's what we're talking about, is the flow of the river. You're welcome to use the word flow. That's like exactly the right word to use here. But in many contexts, we won't know the right word. It'll just be something we haven't had experience with. So I'm not going to use the word flow here. 30 seconds after midnight, the number of gallons passing over the falls is increasing because that's a positive 3 at 3 gallons per minute. Per second. Thank you. So as I'm grading things like this on a quiz or a test, I'm going to be looking for a couple of things. Number one is the units for that derivative. So definitely get gallons per second into your answer. A real common thing that people sometimes don't include is that 30 seconds. You can't just say the water is moving at 3 gallons per minute. You got to say at this one moment in time, 30 seconds after midnight. I have no idea what's happening 29 seconds after midnight or 31 seconds after midnight. We don't know that it's always 3 gallons per second, just at that one moment in time. Okay, next page, number 7. Suppose that R is equal to dg dt, where g was that waterfall function that we just looked at before. So now what I'm interested in is the units of dr dt. So this is one level of derivative beyond what we looked at before, because r is a derivative, and now I am taking its derivative, okay? And so let's just think about the units for dr dt. Well, the units are always the variable on top's units over the variable on the bottom's units. On top, what are the units for r? Looking at our definition, is gallons per second. Those are the units for r. We saw that before. And then the units on the bottom, seconds. So the units for dr dt are gallons per second. And you're welcome to change this if you want. This is really gallons per what? Second squared. And that might remind you of meters per second squared, right? The acceleration. But seconds squared has no meaning for me in any context. I cannot fathom what seconds squared is. It's just an algebraic construct, right? We can multiply seconds together and combine them. But for me, I have a lot more meaning with gallons per second every second. That makes sense to me. So let's see if we can interpret here. What does this mean? dr dt evaluated at t equals 20 equals -2. So something is happening at t equals 20. Let's start our sentence there. 20 what? 20 seconds after midnight. Okay, something is happening. Let's see, -2. We've got our units for -2. -2 gallons per second every second. Josh? The rate of flow is decreasing at 2 gallons per second every second. Yep. Yeah, all good. Let's see, can we write a sentence that doesn't include the word flow? Because even though that's exactly the appropriate word here, we might have context where we don't have one. 20 seconds after midnight, the rate at which water is passing over the falls decreases by 2 gallons per second every second. Yeah, I like that sentence. I really like that we've written out the word every as opposed to just smushing it in with the unit. It's 2 gallons per second is how we're changing, and that change happens every second.
Kind of weird though, because at 21 seconds it could be slightly different. In a way, it's not every second.
It's not every second, but at that one moment in time, this is the reality. Yeah. Yeah, it's good. So why do we use the word decreases here? Because it was -2, right? Not +2. Yeah. You could say this second, but traditionally we would say every second. The fact that we have no idea what's happening any other time is like we've got it right there. To say this is all we're telling you about is that this moment, this is our reality, is every second the flow is changing by 2 gallons per second. Yeah. Yeah, and it's good. So I mean, but it's a nice thing to think about. So for example, suppose that at some point the flow is I don't know 17 gallons per second, just at one moment in time. So if this were the reality and it was just constantly negative 2 gallons per second change every second, then what would be the flow 1 second later? 15, and then 13, and then 11, et cetera, right? So we're just looking at the way the flow rate is changing. But as folks are pointing out, we don't have any information that says it's always 2 gallons per second. It's just at this one moment in time, and it could change. Right? And you might say, well, we're being nitpicky. 1 second is not that long of a time period, and how much really is the water flow going to change in 1 second? Okay, fine. So suppose you're driving down 91 and you're going 65 miles an hour. Are you comfortable saying that exactly 1 hour from now you're going to be 65 miles from where you are now? Right? I mean, you're never going 65 miles an hour for more than a moment, right? And if you stop to get some food, then all of a sudden all bets are off. And if you speed, then it's different. And then when you get pulled over, that's different too, right? So like 65 miles per hour, an hour is a long time to wait. Well, you can argue the same thing about a second, right? We don't know anything other than this one moment in time. Okay, there are 2 group activities today. We have 43 minutes and change, and you're going to use every one of them on these 2 activities. So let's see how far we can get.